Hello, everybody, and welcome to yet another episode of Undercooled, a materials education podcast. This time, Steve and I are on location in Las Vegas, Nevada, and conferences being the magical meeting places that they are, we bumped into an old friend and wanted to bring a special guest onto the podcast. So, Steve, how about a quick intro?
I was so happy to run into Jerry. This is Jerry Floro from University of Virginia, and I've known Jerry for decades. And so hopefully Jerry's going to tell us a little bit about the arc of his career, starting with where he went to college, how he got jobs, and mostly how he even got interested in material science. Because like many of us in material science, we didn't start there, right? Tim was a physics major. I was a math major. How did I get here? And of course, Jerry, turns out, was a physics major. Yet we're all doing material science, and we really think of ourselves as material scientists now. So, Jerry, why don't you tell us a little bit about how you got to where you are now?
Okay. So, yeah, I am going to preface this by saying these guys caught me cold in the hall. And so I was totally unprepared for giving any sort of a podcast or video interview. But, yeah, happy to chat. So I think the lesson already to be learned is there's no linear arcs in science and engineering in terms of careers and education. I started as a physicist, bachelor's degree, Colorado State, a long time ago, and went to grad school for one semester in high energy physics, thinking that was the frontier and that's where I wanted to be. Really hated it and ended up dropping out. And as an undergrad, I had been working in a lab doing research with one of the faculty, something I really like undergrads to do because it's really differentiating and a game changer. And my lab mentor, who was a grad student, had gotten his PhD and went to IBM Yorktown to do research. And so when I dropped out, I called him and said, I dropped out of college or grad school. And he got me an interview at IBM Research, and I got hired there. And I spent 3 years there doing thin film deposition, basically as a service for other researchers who didn't have thin film growth. But I got to learn about all their projects because I asked a lot of questions. And that's when I first heard about this thing called materials science. And as I looked into it, it's like I had all these questions about the films I was growing and their structure and why they grew the way they did. And it turned out this crazy material science thing seemed to have a root for answering all those questions. So when I decided to go back to grad school after 3 years at IBM, I went in for MS&E. And I went to MIT, worked for Carl Thompson doing grain growth and thin film studies. But I think more importantly, just getting really good grounding, both in fundamentals, because I think irrespective of what you do your PhD in, your fundamentals are what carry you on. And I guess that would include the fundamentals of doing research, right? Anybody, I think, can learn to do experiments, but doing research is a very different enterprise. And so that's kind of what I got from Carl and from my time at MIT. Went to Sandia National Labs as a postdoc, managed to stayed for 14 years. And then an opportunity came to apply for academia, specifically at University of Virginia. And I kind of thought about it, and I'd been coaching soccer, youth soccer, for 14 years. And it turns out that coaching soccer actually informs a lot of the ways I approach teaching. I thought I would be a good teacher. Maybe not so good at getting research money, but a good teacher. And so, I came to Virginia. It was 2006. It's hard to believe it's been almost 20 years. And I'm now the associate chair for academics and the director of the undergrad program and the ABET coordinator. And still doing a bit of research. So that's my arc.
That's fantastic. You're way too modest, Jerry, because I know that while you were a lab tech at IBM, you also were one of the first people to recognize solid state ignition by solid state diffusion, creating these reactive foils when you were trying a variety of different methods to make silicides. You saw your film blow up. And that's kind of cool when something blows up.
It's a quick story. You want me to tell it?
Yes, I'd love to hear that
So literally, a pretty eminent scientist named King Tu asked me to deposit rhodium silicon multilayers. So they were doing calorimetry studies. So they wanted lots and lots of reacting interfaces. So I just grew a bunch of rhodium silicon alternating multilayers with different periodicities. And when I took these 2-inch wafers out of the evaporator, they had all these weird kind of shiny places and all this different strange optical reflectivity. And I put this under an optical microscope and I saw all these crazy spiral patterns. I don't actually have these images anymore, and it really makes me sad because the geometries of these things were weird. And so long story short, we were able to show that they had reacted to form rhodium silicide in the evaporator. Basically, when little molten spitballs came out of the evaporation pool, hit the surface and heated it up, and then it just reacted, but it reacted by releasing exothermic heat of reaction, which then reacted the next bit, which reacted the next bit. And for reasons I don't fully understand, these didn't propagate as circles in the thin film, but as spiral patterns. And,
I believe Dave Adams has written many papers on the spiral propagation of these reactive foils.
I believe it. Dave's a really sharp guy. So yeah, I published a couple papers on this kind of solo because it really wasn't my job to do that kind of stuff. But yeah, it was super interesting and super curious, and I think helped get me into grad school. So
yeah, because I know your advisor, Carl Thompson, an amazing scientist. He actually read your papers. And that's one reason why he hired you.
He did. He read them and probably dismissed them too. But yeah, one of his other grad students saw all these weird things happening in nickel silicon multilayers. And I, during group meeting, raised my hand and said, I know what that is. And Carl said, oh yeah, those things you wrote. I guess I should read those. So it wasn't quite that linear, Steve, but yeah, it worked out that way.
But of course, the rest of the story is that it was independently discovered at, I guess, Lawrence Livermore Labs by Troy Barbie, who is making X-ray mirrors. And X-ray mirrors are multi-layers, and they started reacting and blowing up. And then he hired one of Bill Nix's students, Tim Weiss, who furthered that work. But unlike you, they patented it all.
Oh yeah, no, Tim.
And Tim started a company.
Done tremendous stuff.
And Tim's a great guy, and I ran into Tim at the meeting too. So anyway, you go to Sandia, and again, modestly, you don't mention how you made your multiple optical beam sensor with Eric, and that was incredible work. And it got licensed by people at Michigan, by Roy Clark. And Roy built this huge business called K-Space around that IP transfer that they paid. So you never got the money, but Roy did. He's doing very well. He has a horse farm.
Yeah, well, entrepreneurs are a special breed, and I don't have an entrepreneurial bone in my body. So better left to them.
You really got into education. And I know you've spoken at many of the MRS education symposia we used to have. And I always thought you had amazing ideas. So maybe you can talk about some of your earlier work that you did with active learning.
Okay. So at University of Virginia in the material science department, we teach an intro to material science course. And actually it gets taken by a lot of engineering students, not just MSE focused folks, because it's a science elective basically. So about 2/3 of the E-School were passing through this class. And I would typically have enrollments of 80 to 120 in my section. We taught multiple sections. But yeah, it came to a point where I just kind of felt there has to be a better way to engage the students. And I didn't know what that looked like, but I went to this week-long course design institute held by our teaching center. And basically that whole week, they just make you write a syllabus, but they make you think about every single piece of the syllabus and very much in the context of evidence-based active learning and then how you assess. And so I thought, okay, I learned about this thing called process-oriented guided inquiry learning, POGIL. I said, I'm just going to take my section and like modular, take out lecture and put in guided inquiry. That was my thinking going into this thing, because it sounded like an interesting way to teach. And once I got into this this 1-week teaching institute, I realized that really, while it would have made a nice experiment, like I've got a section teaching, 4 sections teaching lecture and 1 doing guided inquiry, we can in theory use all the same assessments and have a side-by-side comparison. It didn't actually work out that way. And I think it's okay, because as I realized that in doing guided inquiry, my goal was better concept learning, especially for the large fraction of students who weren't going to be MSCs, right? Not sort of factual learning and algorithmic problem solving. I mean, those are important too, but concept learning was kind of my, in 5 years, would they remember process structure properties? It's kind of really what I wanted. In 5 years, will you still remember this idea that processing begets structure, begets properties, and so forth? So not only did I change the lecture to this guided inquiry where students essentially construct knowledge in real time during the lecture section, but I changed all the assessments as well to focus on, how do you assess concept learning? And then also I wanted more project-oriented work built into the course, not constantly, it's not project-based learning entirely, but I wanted several projects that students had a slightly more authentic learning situation. They have to work in teams for guided inquiry anyway, so those teams that were in the classroom sections are also the external project teams. And then we even built a final video project in where you had to make an 8-minute video on your favorite topic in material science. We only did that for a few years. And that was quite some time ago, but they've got like 500,000 views, even though it's been static. I only had two years of this. I got away from it for administrative reasons more than anything else, but I actually really loved it because the main requirement of the video was somehow, whatever material you choose, work in the process, structure, properties relationship. And, they make this 8-minute video and it's on YouTube. They can rewatch it. And I figure that's a great way of ingraining this somehow into their, like tattooing it on their brains somehow. So I'd like to go back to doing that actually at some point.
Yeah, I love hearing about the huge variety in this course, with just mixture of different instructional techniques, different assessment techniques, but also just different work that the students can actually engage in to meaningfully use these concepts. And so you mentioned different assessment strategies for trying to probe their conceptual learning better and not have everything just be, end of chapter problems, essentially.
Right.
Can you talk a little bit more about what you did for that assessment?
So there were 2 things. One, we did a online warm-up before every class. And the warm-up was offered through this software, Learning Catalytics, which I know, Steve, you're super familiar with. And it was meant to be kind of just a simple, engaging, qualitative question. They were told it should take less than 2 minutes to answer it, and they shouldn't go to a book or online to answer. Just, what do you think the answer to this is? And gosh, it's been a while since I've done this, so I'm going to forget some of the questions. But yeah, and then we would discuss that, and often it was, the warm-up led into to whatever the topic was we were talking about in the day. And we could actually spend 15 minutes kind of reviewing some of the answers and talking about people's conceptions, what was being asked, what do you think this was about material science-wise, and where have your experiences diverged from what the scientific correct answer was. And so it made a great way. And then these were all participation-based. There's no, getting graded for the wrong answer. And then in our exams, I replaced, there was like 60% multiple choice to be fair, which is tricky. But I replaced those with short answer questions. And the short answer questions were entirely designed around concepts and no calculations, and meant to be 5-sentence answerable, and also meant towards the end of the semester to combine things like phase diagrams, producing microstructure, producing mechanical or electrical properties, and putting that all together in one smallish, elegant problem. And then the final thing I developed was a materials concepts inventory. And there are a few of these floating around. But I designed one kind of based on these concept questions I had developed for the class. And Even though I'm not teaching this class now for the last few years because I've started teaching other things, I continue to offer the concept inventory to all the sections that take this class. And someday I'll do something with that data.
Yeah. As you're describing this process, you mentioned earlier the connection with your coaching experience as well, and how that influences the teaching that you do. And certainly in this more engaged format where students are working on a project or where they're actually having to have group discussions about things that they do and don't understand, there can be some tricky conversations that come up. And I'm curious how your coaching experience sort of supports you in your ability to do that, where some faculty may not feel as comfortable having these very ambiguous open discussions, but how did that experience prepare you to do this?
Yeah, no, I mean, that's a great question, and you're right. Curating ambiguous discussions can be non-trivial, and if you get super uptight about I have to get to chapter X by day Y, it's problematic. So I threw all that away. But in coaching, to me, the goal was to put kids in situations that challenge them to learn kind of in situ. And so, yes, you do some pre-instruction, get some basics, do a little bit very constrained work that's very unrealistic, right? But pass back and forth to each other with nobody trying to stop you. But then creating pressures, or whether it's time or space, to try to make it harder. And that's kind of how I think about the teaching too. You do things, you do them without penalty, you do them to be formative. You have discussions, you have conversations. Then you maybe ratchet up the intensity through the assessment process or through real-time questions during class that have both a participatory component and a correctness component to the grade. I really want students to learn rather than learn to get the GPA. And so I've taken a lot of heavy-duty grading out of the class as much as I felt comfortable with. And I know that level of comfort is different for every faculty. But I felt like there was still rigor. And yeah, I think it's fine.
So I'm going to go back a little bit to your concept inventory test.
Okay.
This is something that many people have tried, but I've never heard of anyone who actually felt it was starting to work. Is this available for other people to access?
I mean, I'm more than happy to make it available. Do I know that it works? I'm not, I didn't design this with like a rigorous educational study in mind. I did it mostly for my own purposes. But as we analyzed the data after a few years that we had, and I would say that if you just looked at the average on the concept inventory, the lecture sections and the guided inquiry sections, because eventually another professor also adopted this, it was always a little bit better, but I'm sure statistically not that much better for guided inquiry. But as we looked at specific topics and specific topics basically, there were some of them, including binary phase diagrams, where it seemed like the performance was hugely better. And we didn't understand why. And I'm not sure if we still do today, but.
Would you be interested in, say, working with another materials department, like, say, Michigan, where we might be able to offer a similar concept? I mean, the value of the physics concept force inventory was that it was done all around the world.
Right.
And they were able to find norms, so you had something to measure your students against.
Right.
So I think that would be, if it's a good inventory, that could be really awesome.
And so the hard thing about MS&E, right, the force concepts inventory that's done in physics, people have some intuitive ideas about forces. So you can ask questions that students have a shot of answering, never having taken a physics class. In MS&E, it's tough, right? You can't just show them a binary phase diagram and expect them to get it right. So yeah, it would look like our gains are huge, right? So I only offer it as a post. I only offer it as a post-exam, not as a pre, because I don't see the value in the pre.
Got it.
But again, it is very much focused on concept and not on calculation. Is it effective, Steve? I still don't know. So that's where I'd love to have somebody interested in thinking
I
about.
think the TMS Education Committee ought to be interested in this. I don't know. What are your thoughts, Tim?
Well, I was just discussing with another colleague down the hall about doing more with the education committee that is really focused on teaching effectively and not just sort of offering educational program, but what do we do in our classes that other people can adopt and share and really get more of a best practices interaction
Oh
going.
yeah.
So I think this would be a great example of that kind of topic to bring to this environment. So another topic of modern importance to our special guest, I heard you have a new undergraduate program.
We do.
So I imagine there's some growing pains associated with starting a new degree. What has that experience been like? Just get us, caught up on the story to date.
Okay. So for context, we've been a materials science and engineering department, since about 1964. Actually founded by Doris and Heinz Woolsdorf, who are pretty well-known people back in days of materials plasticity. And so we've always offered PhDs. And we actually had a fairly significant undergraduate teaching portfolio. So we ran this engineering science non-accredited major, which was kind of a designer major, like 2 super minors. But yeah, through that, we had like an MS&E minor. And so we had a fair number of courses. And over the decades, there were debates about starting an MSc program, and a lot of the faculty didn't want the hassle, so it never happened. And finally, some of those folks retired, and new young faculty, full of energy. That's not me, but came in, and it finally carried the day. So in 2021, the program officially kicked off, January of 2021, and so we're 5 years old now, and we actually graduated students that semester. Because they had essentially double majored, and they had all the credits they needed essentially to graduate. They didn't have an MSc capstone, but they had a capstone. And that allowed us to get into the ABET accreditation cycle quickly too. But okay, so I don't think there were any real surprises on the teaching side. We had to develop a couple lab courses that we didn't have prior, and I developed one of those on a materials properties lab, which I teach today still. The accreditation process, and maybe I won't talk so much about that, but that was certainly exciting. We did get accredited. It wasn't trivial, I will say that to you, but we did get accredited. But I think us, like even existing MSc programs, the challenge was in recruitment. At University of Virginia, all the engineering students come in as engineers, generally speaking, and in March of their second semester, they make their choice of what flavor of engineering. And we had like a group of 8 kids declare, and I said, this is going to be so easy. We'll be 8, then we'll be 9, and we'll get up to the typical kind of 3%-ish of the engineering school that most MSc departments tend to be. But then next year it tanked down to 4, and then 4 again, and then 6. And yeah, it's been hard. We just had our largest recruiting class now in our 4th full year of recruiting. So we had 14 come in. So we're up to like 40 something students, which it needs to be bigger. But how do you get them? And every university is different, but this is also during the time when CS was starting to just gobble students alive. And, they were almost, at one point, even last year, nearly 45% of the engineering school were CS. So
Yeah, it's similar in Michigan. It's shocking how all the lemmings are following each other over the cliff.
You said that.
Well, I just feel that a materials
Sustain so many.
Exactly.
I just feel that it's much better for a student to learn computer science within the context of another engineering discipline. All engineering disciplines have been revolutionized by computation. And so it doesn't matter what department they go into, there's always going to be a serious fraction of the faculty are really computer scientists as well as mechanical engineers or material science engineers. And I know Leo Ziegler at Virginia,
Right.
and he does ultra fast laser stuff like I do, but he's a real good computer scientist and a really good, physicist, material scientist.
Yep.
So,
Yep.
a student who went through a materials program will learn very serious machine learning techniques, AI,
Yes.
as well
They
as
will.
coding, but coding for a reason. Like, who cares if you can build a word processor or a web browser?
Right.
So
Yeah. Right.
we're trying to sell that to students too. And we have just the same problem you have. So what ideas have you come up with recently to try to fix this?
Well, I think if there's a magic bullet, I certainly haven't discovered it. I think it's a combination of factors. Honestly, Steve, I think there's a certain, if you can just keep steady and maybe grow slowly, eventually I think there must be a critical mass you reach where there's enough buzz and the department looks big enough. Students can be risk averse and their parents can even be more risk averse. And it's like, ooh, I really like that material science intro course I took, but I really don't know what the jobs are. And my parents are really saying, oh, you got to do something safe, go do mechanical engineering or whatever. And so I think it takes time to overcome that. We've tried to put in a few more kind of attractive feeder courses that first years might want to take. So in addition to the Intro to MS&E course, we have an Intro to 3D Printing and Additive Manufacturing course, which is super popular and could easily be 2 or 3 times the size if we had enough 3D printers accessible for the project work. And it's, that was started more out of faculty passion than that as a we must have this for recruitment, but it's been, I think, it has an impact in recruitment. Similarly, we have a science of cooking class. So essentially soft matter, and it turns out we had a new student support building with a nice teaching kitchen in it that you can do your lab work in and eat your lab reports. So yeah, science of cooking, again, if we had more kitchen space, could easily double in size. I have no doubt about it. And also a 2000 level class. So, no prereqs, easy entry. And we're now, part of the reason I was here and part of the reason I met you two is we're interested in like a materials maker space that we might create, and maybe some 1 or 2 credit module classes that are, sneakily material science, but on the face of it, hands-on stuff like bladesmithing. So, but that's a pipe dream. We'll see how that one goes. But so that's, I think, our main effort is how do we convince first years to become MSEs? Then the big effort also is we don't live in an industrial setting at all in Charlottesville, Virginia. It's rural, it's a small city. There's not a lot of heavy industry. It's not like Purdue and Indiana and the steel industry. So how do we get kids in high school in Virginia to know about material science? And so that's a hard thing, but we are doing our first ASM materials camp for teachers this summer. I'm running that. And I think that has a lot of promise, actually. And I've gotten a lot of teachers already enrolled, and I hope to get some more. And you feel like if you could do that every year or every other year for 10 years, you have a chance of diffusing out to a lot of high schools. And then the third thing, and I think this is an interesting avenue, is I was co-PI of an REU that just ended last summer. And in this REU, we promised that we would take half of our REU cohort from local community colleges. And it was an absolute promise, right? It's easy to say that and then, ooh, I want to grab kids from, the biggest material science programs in the country because they're great to have in my lab. And in fact, we ran an average of almost 65% of our 3-year cohort being from community colleges. And you know what? These kids are fantastic. They want to learn so much, and they work together so well, and they're so collaborative. And so, number one, I just loved working with them, and I think it's a great untapped potential, just in general. But we're starting to see transfer students as a result, because in Virginia, probably true in Michigan as well, if you get your associate's degree with a certain GPA, you have guaranteed admission into one of Virginia's state schools. And I would go up every year to recruit from our partner schools and do MSc demos and all the good ones, shape memory metals and metallic glass trampolines and so forth. And yeah, super effective. And I think these are wonderful students to bring in if your curriculum can handle transfers coming in halfway through, which isn't trivial either.
I love that idea of engaging more with our community colleges to help bring in more students. That's something that I see a lot of discussion around at ASEE, the American Society
Hmm.
for Engineering Education, but I don't see as much discussion about community colleges in the material science professional societies.
Yeah.
So this could be a really important avenue for us to investigate for getting more students. As far as the teachers camps, so we just started something new at Michigan this year that you might be able to start doing in a couple years, which is we've started reaching out to our teachers who did the camps
Okay.
with us, and now we're having them bring their students to our department as a field trip.
Okay.
And so I get to, just text whichever teachers I've still been in contact with since they came and did the
Uh-huh.
camp and said,
Yeah, yeah.
"Hey, do you want to bring your students?" And they say, "Absolutely. I would love to have a free field trip."
Oh, yeah.
And
That's a great idea.
we had our first one actually just last week. It was a huge success. I already heard our teacher reported that 2 of the students said, "All right, I want to be a material scientist now." So, everyone counts. Absolutely.
Everyone counts. When your numbers are small, it makes a difference. And MSc will never be huge. And in some ways, I like not being too large because, like my labs, we can be much more hands-on. It's not a team of 10 kids with one doing something and 9 with hands in pockets watching. Everybody gets to use instrumentation, do experiments, process, characterize materials. But yeah, you have to be a certain size in order to have a critical mass and to be stable. And it's a hard challenge.
Well, I applaud your efforts at running an REU. I think it's great. I've run one for many, many years. And although we're not taking students from community colleges, because this is a national program,
Right.
We're usually hitting 70% students who are coming from schools where research is not the
Right.
primary focus.
Yep.
And you are so right. Some of these kids are amazing.
Oh,
Because
yeah.
guess what? In these small schools, they have amazing physics departments.
Right.
It's hard to get a job as a physics professor in a research
Yep.
institution, but the quality of the faculty at these small non-research schools is incredible. And all they do is teach, and there's a little heavier emphasis on theory. So a lot of them come in thinking theory is
Yeah,
king,
right.
and then they get to do experiments, and they see it's really cool to do experiments. So that's awesome. And talking to you, have you ever been to one of the NAMES meetings, the North
been to one.
American?
Just one.
Just one.
Wonderful meeting. Yep. I've been to one.
Well, I think you have a lot of amazing ideas. It would be great to hear you. There's the next one's close to you. It's at Georgia Tech.
Oh, wow. Okay.
And the deadline's like in a week or two to put in an abstract.
Okay.
And we
Yeah,
made it relatively inexpensive. So it'd be great if you could come down, and we'll probably be there. I'm hoping it's in the middle of the first week of August.
Okay.
So hopefully
Nice
you
cool
can...
time in Georgia.
Yes. But it would be wonderful if you could come and talk about some of these things.
Okay. Yeah, that's actually an interesting idea. Yeah, I had talked about this guided inquiry thing at the last names I went to, but that was a long time ago. So
Yeah. But it would be awesome to hear your ideas about attracting more people to material science. I think your ideas of 3D printing, I've never heard that idea. That's a great idea. We might steal that idea. And the food science, I love that. When I came back from sabbatical from Livermore, my department chairman made me teach the lab. I'm going like, what do I know about I was a math major. I never
Right.
had. And so, but what do I know? I know how to do research. So I did a whole lab because I had gotten into coffee. Because Oakland is the mecca
take that
of
class.
specialty coffee.
Right.
So I made a module on, you've learned how to use all this equipment. Now can you use it to tell the difference between really disgusting Vietnamese Robusta versus 1,400, meter high, Guatemalan coffee.
Yeah.
And so they're like, so what do we do? It's like, I just told you.
Yeah, right.
And they were very upset with me that I didn't have, a step-by-step guide. And so I told them, look, you can roast coffee with a heat gun dog bowl technique. You can get rid of the, chaff with a snorkel hood.
Yeah.
You can pull coffee out at different times of the
I'm
roast.
definitely taking this
And you
class.
can look at it in an X-ray diffractometer. You can look in the, optical and in the SEM. And, made me quickly realize why I hate French roast, because guess what? It's called graphite.
Ah,
You see these broad amorphous peaks early sharpen up. And by the time you get to a pretty French roasty, very sharp, distinct peaks that all
really? Well, that's
index as
fascinating.
graphite.
That's fascinating.
But it was so
That's
much
crazy.
fun. The differential scanning calorimeter was my favorite, because you put a little in. First, you see an endothermic peak for all the water coming out.
Okay.
And then you see this, bam, this huge exothermic peak right at the temperature where the roaster and the students could hear this. You get the first crack. It's like popcorn, because you get fats and lipids and
Right.
stuff, evolving CO2 that bursts out. Then there's nothing. Then you see little tiny ones. That's the second crack, where it's additional exothermic reactions. And there it is in the DSC. And so I get so excited by that. And most
Oh, yeah,
people
it's
look at me and
fantastic.
say, "What's the matter with
I
you?"
had no idea, honestly.
It's
So-
really cool, and you can see all of this. So you should try that in your
Yeah, I'm
in your
gonna
food lab.
tell our faculty
Because
for sure to
food
look
science
at this.
is so connected to material science.
It is, and right, it's amazing what you can do with simple materials and relatively simple, low-cost apparatus, and still learn something really fundamental, conceptual, and insightful from it. And I think that's the beauty. You don't have to have $2 million of lab equipment to do really good work.
Yeah. It's so funny this came up because just last night the students were asking me, so what class do you want to teach? And the first two things I said were the materials of food science. And then the second one was the materials of music. Why do we build musical instruments out of the things that we
Right.
do? And there's so much there because, there's all the electronics for
Yep.
electrical instruments, but there's the acoustic properties, there's all of the material selection, and even material sourcing questions of, if we take wood from different types of trees, but even different places on Earth, how do they have different acoustic qualities, and how is this driven ultimately by processing?
And
It's
is it
the environment that
sustainable?
they came from, right?
Right.
And is it actually sustainable? Because just because it grows on a tree doesn't mean it's sustainable.
Especially if it grows
So-
in the Amazonian rainforest, right? So, yep, these are great questions. Yeah, materials for athletic equipment and sports too, right? So I think there's a lot of great ideas out there, and I think a lot of people are doing wonderful things around the country and internationally. And yeah, it's hard to sort of
There's never enough
Figure it
time to
out.
do all the great things that
you
we want to
can't
do.
even figure out what all the great things are because there's just so much, and it is distributed. So yeah, TMS ought to do more of sort of getting
Well,
that
that's
together.
one reason we're doing this podcast. This will
Great
help
idea.
other departments hear these ideas. Hopefully, you'll listen to a few of our other podcasts and hear ideas from other people. And that's, kind of cool. But, I always have a special place in my mind for University of Virginia. Of course, I had good friends besides yourself who went there. Robert Hall went there, and
Yep.
he was a good friend of mine from Bell Labs. And, Eric Stack was a graduate student there. And
Yes.
now he's making all these amazing TEM in situ holders. So, and so there's, you
Dave,
mentioned
right?
the founders.
Right.
Right. So Virginia's got a real special place in the impact on material science, and especially one guy whose papers I read when I first started as a postdoc at Bell Labs, looking at strain in thin films, the Matthews Blakesley paper. But of course, when Matthews was there, he had a son. And from what I understand, he did pretty well in the music industry. Maybe you can
Right.
tell us that story.
So I didn't know this either. So I have John Matthews' little blue monograph on epitaxial growth in thin films, and especially dislocation-based plasticity processes, misfit dislocations. And so long before Virginia was a twinkle in my eye, I used that book kind of as a Bible for my epitaxial thin film growth research. And yeah, I didn't know this right away when I got to Virginia, but yeah, John Matthews came to work with the Wilsdorfs and one of their former students, now faculty, Bill Jesser. And John Matthews ended up staying, I think, in Charlottesville for quite some time as a part of this. And I should be more conversant with the details of the history, but I'm not. So, but yeah, his his children ended up growing up for a decent portion of their lives in Charlottesville, and one of his kids did have musical talent. His name was Dave, and went on to form the Dave Matthews Band. And most people, I think, even youngish people, will have heard of that. I don't know. Kids are getting younger and younger, and Dave Matthews Band's probably getting older and older. But yeah, it's an interesting connection.
He was just inducted in the Rock and Roll Hall
Which
of Fame.
means he's getting older
And
too,
so
right?
that's kind of cool.
Yeah, and so they supported the building of Wilsdorf Hall, so named after Doris and Heinz, and they established a Matthews epitaxy lab basically in our building, and yeah, so it's a great piece of trivia, but it's interesting to see these connections, right? So music, right, coming in on the heels of material science.
Yep.
So.
Well, as a literal rock star institution, is there anything else that you'd like to just share with the audience? Anything you want to talk about, current developments, or just anything you want to get the word out about before we wrap this up?
Yeah, I mean, I would say if you're hearing this as a high school student or hearing this as someone who's about to graduate with their bachelor's degree, there's many, many great universities out there. Virginia, I would simply say, is one of them. And depending on what kind of a lifestyle you like, Charlottesville, Virginia is kind of nestled at the base of the Blue Ridge Mountains. We are a smallish university of about 24,000 people and a decent-sized department professor-wise, but always looking to add more students. But we work really hard to create a community and look after our students, both undergraduate and graduate. Obviously, and I think all faculty have to feel this way, their success is our success. Right? We want our students to be successful. So yeah, think about us too.
Excellent. Well, thank you so much again for being our guest today. It was a great conversation. I know we jumped on this last minute, 0 minutes to spare, but this was really enjoyable. Thank you so much for coming and being here today.
Thanks for having me.
All right. Thanks a lot. We'll
All right,
see you
guys.
later.
Take care.
Bye.
Bye.